Hello everyone. Here's a lecture about electrical impedance and how we can use these physical phenomena in a medical area. Well, uh, we have two goals here. First one is about the basic part, about the terms and definitions that I use it here in the basic physical concepts, like a direct current, like a resistance, like an alternating current, and impedance itself. Also, we need to mention how it's originated in the human body. What is the real source of electric impedance in our bodies? And furthermore, we go to the next goal of the story. It's to describe diagnostic technologies that use these physical phenomena, exactly said by impedance. Those technologies are quite similar, but there are definitely still some differences. We need to go deeper there and figure out some details about these quite versatile technologies. So here we go uh, to the basic points of the story. Well, again, we need to start from the basic physical concepts like a direct current and alternating current. After more, we need to go to the conductance and resistance. And even more complicated idea again at the impedance itself, influence of the resistance and reactance into that overall phenomena. And the last part is a particular stories about four technologies given here. So let's go for the basic concept of the direct current. I hope really everybody are familiar with it because it's really simple thing. We can find that electric charges move in one direction. That's what we mean by the term direct current. But look, once we said they flow, we need to mention another term. It's a conductivity or conductor. This medium that's suitable to provide appropriate environment for such movement of charges definitely should be called conductive. So current flow through the conductive medium. Direct current is a special kind of electric current when every charge goes in the same way. In contrast, alternating current demonstrates for us some variability, and we suppose that it's a periodic process, some sort of oscillation, and these oscillations typically happens in a harmonic way. What do we mean? So we can represent it as a sinusoid or cosinusoid if we talk about the graph, or if we talk about the visual representation of this. It means time after time, charges moves in an opposite way. In a one half of the cycle, they go in one direction. In the other half of the cycle, they flip on the other side and the other way. But look, why this happens? Why alternating or direct current happens? Why those charges need to flow through the conductive medium? And there is a very simple answer. We know it as an electromotive force or applied voltage. So that's the real reason why current appears in a conductive medium. Voltage and force charges to move. And in a case of the constant disbalance of the field, electric field indeed, or difference of electric potential, we have direct current. If this difference of electric potential in 2 points of the system is changing, we talk about the alternating current. So as you see, it's a quite simple and basic idea. But when charges move through the conductor, they will always meet some opposition. And this opposition is known as a resistance. Well, here are two opposite terms. In one hand, conductor, suitable medium for charges to move. It have conductivity. It's a measure how easy to pass through it for the charges indeed. And on the other hand, the same conductor could be described by the term resistivity. How complicated to pass for the charges to pass through that medium. So resistance of an object in a given circuit could be calculated through the Ohm's law, and you can see it here. So resistance in a circuit is the ratio between the voltage, again it's a driving force, it's electromotive force, something that pushes these charges through this particular object, And in a denominator, we have current itself. So it's an outcome, how effective this electromotive force is. So resistance, it's a measure of the balance. And now I want to highlight this fact that resistance is inversely proportional to the current. Well, it could be explained in a simple words like, if there is more obstacles on the way for these charges, we will have less current. Less of the charges could pass through the conductor. Also, we can claim that resistance could be claimed as straightly proportional to the voltage. So if more efforts push these charges through the given resistance, we will have more current. Well, again, it's a quite basic, quite simple thing. Another approach is to describe object as some real object, and it have some dimensions. And here we go to the next formula. You can see it on the bottom of the screen. So resistance for the object itself could be described as a function of its resistivity of the material in this object, its length. So as you guess, different substances have different resistivity or different conductivity. Some substances are much easier to pass through for the current, some of them not. Length is obviously straightly proportional. If longer paths should be done through the medium, definitely more obstacles we can meet on the way. But here comes the feature. Cross-sectional area is inversely proportional to the resistance. So for the charges, it will be easier to pass if there is a wider or larger, in a cross-sectional terms, object. More chances, more places to go through. If there is a bottleneck or small cross-section, we can meet an obstacle, we can meet a real problem or high resistance here. So here we go to the next step. We should take into account that resistance exists in a direct current circuits as an alternating current circuits. But resistance remains the same with the different frequencies. It's not true idea for all elements in the circuits. And here we go to the idea of impedance. Impedance, it's also opposition force that appears in a circuit of the alternating current. And it depends from the frequency. So we need to consider this option. Resistor, which was mentioned previously, it's a very simple element, and its behavior doesn't depend from the direction of the alternating current, doesn't depend from its frequency. But there are some other options, and they will be highlighted in a further part of the story. To show this special behavior of the elements in a circuit, we need to claim the term reactance. So exactly reactance, it's a responsible thing for the such strange and cold behavior of the alternating current circuits. It's react for the frequency or applied force, electromotive force, lead to reaction in a current that flow through that circuit. So that's a sense that stay behind the word itself, reactance. Well, and it's a also complex thing that consists of two components. And here they are. Such elements that bring special behavior in alternating current circuits, they are inductors and capacitors. Well, inductor, it's a coil, it's a solenoid. Even a wire itself could be considered as an inductor, but its inductivity is extremely low and we often just drop it. Well, for the inductive element in a circuitry with the alternating current, we can claim that its impedance or exactly reactance is straightly proportional to the frequency and the inductivity. For the capacitors, we have opposite relationship. Reactance originated in a capacitor is inversely proportional to the frequency and to the capacitance itself. What does it mean? That those two elements will behave in a different way in alternating current circuits and in direct current circuits. For the DC circuitry, coil or inductor will act as just a wire, just a conductor, nothing more, nothing special. So zero frequency of the direct current will lead to the zero reactance. In contrast, capacitor, which is actually break of the circuit, in a direct current circuit, it will act as a stopping point and charges wouldn't jump over it. So direct current cannot pass through the capacitor. And in this ratio, you really can see it. If frequency is zero, we have infinite reactance coming from this capacitor. But in alternating currents, their behavior depends from the frequency. And for the inductive component, we can explain it by the Lenz's law. Well, when an alternating current, when any current flows through the coil, what happens there? Electric field energy will be converted in a magnetic field that exists around this coil. And this magnetic field, here comes the Lenz's law, it's always fight with the current that originated. And especially said, it fight with the changes of this current. If current wants, in a coil, definitely wants, go higher, this magnetic field will try to suppress it. If current through this coil will go downward to the zero, magnetic energy will turn back into the electric form and supply. So that's why if this process will happen faster or higher frequency, we will meet more obstacles originated in a magnetic field around the coil. For the capacitor, we have opposite story. In a case of the low frequency, electric energy will be stored in a capacitor. It could be considered as a storage device because it's provided two parts of the conductive material separated by the layer of dielectric. And charges will stay on one and another side separated by the dielectric. So negative charges never will go to the positive side, and there is no positive charges, as you know, if we talk about the electric current. But when we change direct current to the alternating current, when we start to change the current here through the circuit, we will find that all the electrons that were stored on one side of the capacitor will move in the other direction through the circuit. So really, in each half cycle of the alternating current, charges never cross the dielectric. They just store it in one half of the capacitor, and in the next cycle, they will be reused to make current through the rest of the circuit. So it sounds rather tricky, but actually it's quite simple thing. Really, charges never pass through the dielectric layer. And the capacitor creates its own electric field that also influences the major circuit. That's why it demonstrates different behavior. Higher frequency means less obstacle. Again, why it happens? Because through the shorter time, this capacitor couldn't be charged so stronger, and it cannot store a lot of energy there to affect the next cycle of the alternating current. Now we will go toward the four technologies that are used in the medical field, and all of these technologies based on one physical action. We're going to measure impedance of the whole human body or some particular part of it, some particular region, doesn't matter. Physically, all of them are the same. We take an ohm meter and we measure the impedance of the human body or its part or particular organ. These measurements done in a slightly different way, but again there is one common thing: we use definitely direct current. But there are the high frequencies. Such frequencies are undetectable by our nervous system, that's why it's painless. If we talk about the 50 kilohertz, which is quite basic value, It's not extraordinary thing. Or 100 kilohertz of the alternating current, or even more, 250,000 kilohertz. It stays beyond the opportunities of our nervous system to detect it. So that's why it's painless. Think about it. Another thing that we use really low current, something like 30 microvolts, or let's say 100 microvolts. Well, it's nearly nothing. And that's why it couldn't make any thermal effect in the human body. And that's why it's bring no hazardous consequences. It's too weak to be damaging agent. That's why all these technologies could be considered as safe. We don't talk about the case when a circuitry is broken and something abnormal happens. Yeah, in this case, any electric devices is dangerous. But if everything goes in the right way, these technologies are painless and safe. And also, for the electric current to pass through the human body, we don't need to penetrate the skin, we don't need to make any incision or whatever. So, here comes another important consequences. These technologies are non-invasive. But let's talk a bit about the bioimpedance or impedance of the human body or even a single part. Now I want to remind you about two components of impedance. It's a resistance and reactance. Resistance, it's a property that always exists in our body. Our body is a conductor. Definitely not the best one, and even not a conductor of the first type based on electrons. We are ionic conductors. That makes our resistance much higher than in a wire in a circuitry. So we have some value of resistance, and it's rather constant. It depends from the metabolic processes in our tissues in our body. It depends from the number of charges, like inorganic ions as organic. Well, we talk about sodium, potassium, chlorine, whatever, any inorganic part, and also even amino acid, even a glucose, it's also ionic species, and they always present in our body. But think about it, all of these molecules, all of these ions, they are rather large compared to the electron, and that's why resistance of the human body is rather high value, and is rather constant. We have homeostasis. Another component of the impedance is the reactance. So reactance in turn consists of two parts, based on inductance, based on capacitance, as mentioned before. But look, about the coil or solenoid, can you recall some structure like this in our body? No, we have nothing like this. So that's why only one component of reactance in a human body, it's reactance based on a capacitors. And now I want to highlight this fact that each our cell is covered by the lipid bilayer. It's a dielectric, definitely. And inside the cell we have intracellular fluid, also known as a cytoplasm, filled with the organelles and other items inside the cell. So we have conductive medium inside the cell, we have dielectric layer that covers the cell, and we have extracellular fluid. Well, it's another conductive part. And finally, we can make conclusion that each single cell in our body, it's a small microscopic one, but capacitor. So in a human body, you barely meet no coils, no inductors of any suitable inductivity. So we can neglect it. In contrast, we consist of billions of the cells. Each of them is a microscopic capacitor. So finally, in a bioimpedance, we can find resistance and reactance. And reactance comes from the cells. Our cells and tissues provide those two components. Now let's go to the particular technologies that exploit this fact that human body have impedance, and this impedance is related with a cell-based structure of human body. The first technology, it's a bioelectric impedance analysis, BIA. Its goal is to evaluate body composition. And actually, we suppose that in the human body we can find water, so-called fat-free mass or lean mass, and body fat. So these components have different as a resistivity, as a different reactance based on the capacitor properties. Well, water itself as a core of our cytoplasm, intracellular fluid as extracellular fluid, it demonstrates nearly constant resistivity and actually no capacitance at all. But our cells, as in the muscles, as in the adipose tissue, demonstrate different behavior. And here comes the feature. We approximately recalculate supposed ratio between these components according to the changes of impedance in a body. So we just plug a couple of electrodes for the human body. Typically, one electrode goes on the hand, another one on the foot, and we measure overall impedance from the limbs and trunk. But we get an electric quantity impedance. Please realize that using the special formula, we should recalculate this into terms of the components, into the terms of balance between those parts, like water, like a fat, and like a lean mass. But there's a problem. There's a great problem and limitation of this technology. These calculations becomes possible only if we assume that human body shaped like a cylinder. Well, obviously, in reality, it's not true. And yeah, we consider it as a set of a cylinder. Let's say arm is one cylinder, trunk another, lower limb is another. So at least 3 or 5 cylinders. Well, cylinder-like shape, but not exactly cylinder. That's decrease accuracy of our calculations. Another assumption is, well, our tissue is supposed to be homogeneous. Just think about the trunk. Just think about even the forearm. Which tissues we can find in the forearm? We definitely can find the blood and skin and the muscles and the bone and the connective tissue and nervous tissue. So all of this is presented in nearly each part of our body. Are they same? Not definitely. But this approach cannot make a distinction between them. And that's why it's another great problem. Lack of accuracy due to this simplification or assumption. And the last one, that condition through the measurement time, it's rather short, it's less than even a minute, but anyway, all of this remains stable, all electric properties remain stable. Yeah, we have homeostasis that maintain all our parameters in some given rather narrow range over the time. We even control our temperature, etc. But it's not true exactly. We are not static system, we are a live dynamic system. And that's why the core assumptions done by this technology, done by this approach, and explaining a relationship between the electric impedance or bioimpedance caused in this technology with a real body composition, they are not exactly real. They are never realized. So that's the greatest problem of this technology. And take a look on a point, advantages and disadvantages. When we talk about some method, diagnostic method, treatment method, doesn't matter. We always should think about the comparison. Why this technology is better than another or worse than another? So this is your question. Please make some records in your copybook to highlight this point. Do you really think that this technology is better than another one because of this, and make some list? And worse than another technology, and also make a list. So what could be the comparison point for this technology? Definitely we need to compare with the comparable things, with the same kind things. For the BIA technology, competitor could be claimed like dual energy X-ray absorptiometry. So that's technology which is based on sending the X-rays through the human body with the two different frequencies and comparing their absorptivity. So this technology have some other problems, have its own limitations, etc. So think about it. If BIA is better in some kind rather than dual energy X-ray absorptiometry or worse. So and please record your suggestions here. Another technology based on totally same physical principle or exactly measuring the impedance of the human body, it's an electric impedance cardiography. Well, its goal is to calculate, again calculate, not measure directly, hemodynamic parameter. Well, like a cardiac output and a heart rate, or stroke volume and a heart rate, it will be sufficient to get a cardiac output, etc. These values are based on, again, calculations, not a measurement. What we really measure, it's just an impedance. We put the electrodes above the thorax, on the neck, and on the lower part of the thorax. And we measure overall impedance of this part of the human body. And we assume that this impedance will change over the time in a rather rapid way. But what could be reason of such rapid changes? It's definitely pumping activity of the heart. When through the diastolic period in the thorax more blood arrives through the venous part, we have more liquid in the thorax. More liquid, it leads to the decrement of resistance. But when systole comes, this liquid will be pushed out of the thorax to the distant part of the body. So overall amount of the fluid in the thorax will be decreased and resistance and internal impedance will rise. So here it is. Another extra feature, it's an arrangement of the RBCs when the blood flow out of the heart. Well, but both these changes are based on a cyclic activity of the heart. That's why we can approximately evaluate, approximately calculate the value of the stroke volume, and also we can measure duration of this process, just measuring the impedance. And here comes the greatest problem of this technology. Again, we not directly measure what we need. We don't touch the blood, no. We just make a conclusion after measurement and tracing the changes of the impedance over the time. We make conclusion about the stroke volume and heart rate. And this assumption, this relationship, definitely not the perfect. So the same very similar problems as in the previous case, as you see. Human body unique for each human being. Yeah, we have some typical plan as you guess, but details are differ, and that's why what we calculate for the one person could be not true for another. It's the greatest limitation of this technology. We never know the real actual value of the stroke volume. We can approximately calculate it. Please realize this thing. So advantages, disadvantages, again, is up to you. And what could be the comparison point? Well, to measure stroke volume or cardiac output, we can find another technologies like a great family of the dilution technology. When we introduce some dye into the circulatory system, and after that trace how it's distributed across the body. It's probably the gold standard in the terms of the hemodynamics, and we can find some problems in that technology. Electric impedance cardiography definitely have some advantages. Okay, please think about it. Compare dilution methods with the EICG. Or another option is to use ultrasonic technology like a Doppler technology, to get the nearly same information. So please again make a list of the benefits of this technology and drawbacks, comparing to dilution or ultrasonic investigation. And we go to the next technology, which is again actually the same. We again measure the impedance, but now not in a thoracic region. Now we go from the center of the cardiovascular system to the peripheral region. It could be even single finger, it could be palm, it could be forearm, it could be leg itself, it could be head. So everything but the thorax. So approach remains the same. We measure impedance. After that, we recalculate some hemodynamic parameter, but for the peripheral region. And that's why problems are the same, exactly the same. We never get the real value, but we can estimate it in a quite approximate way. And here comes another feature. For example, we cannot reach the exactly spleen, and we cannot measure actually impedance only of the spleen. So organs, internal organs, especially said, they are not free from the neighborhood. And for the current, even if we apply electrodes on the surface of the skin, remind you that's non-invasive technology. We not go deeper than skin. We stay on the surface. We never measure solely impedance of only one organ. We always get some neighborhood influence. And we cannot see what is a real trace of the current. As you know, current will always search for the easiest path. And we have no guarantee that it really passed through the organ of interest. That's why it's a great technology for the lower limbs, for example, for peripheral regions. And that's why it's always used. We again have the same problems, we have the same physical approach, and you can find quite similar advantages, disadvantages, and make this list yourself. Technology which can be used for the comparison here, it's definitely Doppler technologies based on ultrasonic beam reflection and even a photoplethysmography in some case. So please make a comparison with these technologies. And the last one in the list, it's an electric impedance tomography. And this technology have two quite different goals. In one hand, we want to get an image that what makes it differ from the previous technologies. In the previous technologies, we get some quantities. Here we want to make an image. So it means this one goes to the category of medical imaging. But another one is just a quantity. We want to evaluate how rapidly and for which volume of the thorax will be changed. So obviously, real and the most obvious reason for the changing of the volume in the thorax, it's a ventilation process. So through the inhalation-exhalation cycle, we have extremely rapid changes of the volume and quite serious. So for this technology, that's why point of comparison could be split it in two parts. For the imaging goal, so to make an image of the thorax, we can compare it with a computer tomography, for example, or MRI. So, and please make this comparison in one side. Why electric impedance tomography better than computer tomography or magnetic resonance imaging, and why it's worse. And another goal is to get volume changes of the thorax. It's mostly for the respiratory control. In this point, comparison technology could be pulmonary function test, nearly in any kind of it. And there are also should be another list, and those goals are different. So again, for this technology, should be two lists of advantages, disadvantages. Principle of operation remain the same. We put a lot of electrodes around the thorax and we measure how easily pass current, alternating current indeed, through the thorax in a different direction. So, but in this case, please realize, we reconstruct the image. We are not get directly some shot of the thorax or something like this. No, we get a measurement of the electric properties in different direction. After that, using the special recalculation procedure, using the special software, we can get a final image of the thorax. Well, this technology have definitely some problem. In one hand, we cannot put the hundreds of electrodes, and that's why we for sure have insufficient spatial resolution. Image quality that is obtained by this technology is really poor. And that's why we barely can use it to visualize something that happens in the thorax. Also, please realize that image here is reconstructed according to electrical properties. That's why this image not reflect our perception. So length wouldn't be red or how we can receive it by our eyes or whatever. It's really out of vision. It's really provide for us image that doesn't fit to our perception because it's a electrical in a quotes image. And another problem is uncertainty. We're not sure how exactly current flows through the human body in the thoracic region. And that's why we have reduced accuracy of the measurement. So now remind you that advantages and disadvantages list should be done comparing with two technologies according to different goals of this one. Electric impedance tomography should be compared with one of the tomographic medical imaging technology like CT or MRI. And in another branch, please compare it with a pulmonary function test. So finally, also please make your records and answer yourself this question. Among these technologies, which one bring the really unique results? Something that couldn't be obtained by another technologies, by another competitors here. Another point, which one of them have a highest accuracy again comparing with the competitors? Could this technology be considered as a really fine tools to get a real knowledge or not? And another answer that I expect to find in your copybooks is it really safe? Could it be considered as a safest comparing with a CT or MRI or other things? So please analyze all your list of the advantages, disadvantages, and make this final conclusion. So here are some references. You can find them in the guidelines too. So here it is.